Right now, as you are listening to this, there is an invisible, high-frequency symphony vibrating through the very air around your head. This isn't some mystical energy. It is a complex grid of electromagnetic waves, pulsing with billions of packets of data every single microsecond. Every time you send a text, stream a video, or even just check the time on your phone, you are tapping into a global machine so vast and so intricate that it makes the Apollo moon missions look like a science fair project. We call them the Gs, the generations of mobile networks, but most people have no idea what actually happens when their phone switches from 4G to 5G, or why their call suddenly drops when they walk behind a thick concrete wall. Today, we are deconstructing the entire history, the physics, and the sheer engineering audacity of the mobile network, from the brick-sized phones of the 80s that could barely handle a voice call, to the ultra-low latency networks of today that can perform remote surgery from across the planet. We are going deep into the wireless abyss. If you have ever wondered why your internet is fast in the city but vanishes in the woods, or what the mysterious 6G future actually looks like, you are in the right place. Let's dive into the electromagnetic spectrum. To understand where we are going, we have to travel back to the late 70s and early 80s. This was the first generation, or 1G. Imagine a world where a mobile phone wasn't a sleek slab of glass, but a 2-pound plastic brick that cost the equivalent of $4,000 today. 1G was entirely analog. This is a crucial distinction. In an analog network, your voice is converted into an electrical signal that directly modifies the frequency of a radio wave. If you've ever tuned an old FM radio and heard that fuzzy static between stations, that is the world 1G lived in. It was incredibly inefficient. Because the signals were analog, they weren't encrypted. If you had a simple radio scanner, you could literally eavesdrop on anyone's conversation by just tuning into the right frequency. There was no such thing as a text message, no such thing as data, and the battery life was measured in minutes, not hours. But 1G proved a revolutionary concept. The cellular structure. Engineers realized they couldn't just have one giant tower for a whole city because the frequencies would overlap and crash. Instead, they broke the map into small hexagons, or cells, each with its own low-power transmitter. This allowed them to reuse the same frequencies in different cells, creating the foundation for every mobile network that has ever existed since. By the early 90s, the world reached a digital turning point. This was the second generation, or 2G. This was the birth of the GSM standard in Europe and CDMA in North America. The move from analog to digital was like moving from a cassette tape to a CD. Instead of a continuous wave, your voice was chopped up into bits and bytes, binary code. This allowed for two massive breakthroughs. First, encryption. Because the data was digital, it could be scrambled, making your calls private for the first time. Second, efficiency. Digital signals can be compressed, allowing more people to talk on the same frequency at the same time. But the thing that really changed the world during 2G was three little letters: SMS, the short message service. Suddenly, you didn't have to call someone to say hello. You could send a tiny packet of data containing up to 160 characters. This was also our first taste of the mobile internet through something called GPRS or EDGE. It was painfully slow, measuring in kilobits per second, but it was the first time you could check a very basic, text-only weather report or a sports score on your phone screen. 2G was the era of the Nokia brick, the phone that could survive a fall from a building and still send a text. It was the moment the mobile phone moved from a luxury tool for businessmen to a universal device for everyone. But as the 2000s rolled around, text wasn't enough. People wanted photos, they wanted music, and they wanted a real web browser. This led to the third generation, or 3G. This era was defined by the transition from kilobits to megabits. For the first time, we had what was called mobile broadband. Technologies like UMTS and HSPA allowed us to actually use the internet in a way that felt familiar. This was the era of the first iPhone and the birth of the App Store. Without 3G, the modern smartphone would never have survived. It was the first generation that allowed for video calling, though at the time it was often laggy and pixelated. The physics of 3G involved much wider frequency bands, allowing for a bigger pipe for data to flow through. But it was also a messy era. Different parts of the world used different standards, which is why your phone from the United States might not have worked when you traveled to Japan or Europe. We were building a global network, but we hadn't quite figured out how to make it speak one universal language yet. Around 2009, The industry realized that the architecture of 3G was hitting a ceiling. We needed a network built from the ground up specifically for data, not just for voice calls. This was the start of the fourth generation, or 4G LTE. The LTE stands for long-term evolution, and it lived up to its name. 4G changed the game by treating everything, even your voice call, as a data packet. This is known as VoLTE, or Voice over LTE. Before this, your phone would actually drop back down to 3G or 2G just to make a phone call. 4G brought speeds that rivaled home Wi-Fi, which enabled the streaming revolution. Netflix, YouTube, Uber, and Instagram all became possible because of 4G. The technical magic here involved something called MIMO, multiple input, multiple output. Instead of one antenna talking to one tower, your phone used multiple antennas to send and receive data at the same time. It's like turning a one-lane road into a four-lane highway. 4G also introduced carrier aggregation, where your phone could grab signals from different frequencies simultaneously to boost your speed. If 3G was about browsing the web, 4G was about living on the web. Now we find ourselves in the era of 5G, and this is where the physics gets truly wild. Most people think 5G is just faster 4G, but that's like saying a jet engine is just a faster propeller. 5G is a fundamental shift in how we use the electromagnetic spectrum. It operates on three different levels. First, the low band, which travels long distances and through walls but isn't much faster than 4G. Second, the mid-band, which is the sweet spot of speed and coverage. And third, the high band, also known as millimeter wave. These are ultra-high frequencies that can move data at several gigabits per second. We are talking about downloading a 2-hour high-definition movie in 3 seconds. But millimeter waves are fragile. They can be blocked by a tree, a window, or even your own hand. To fix this, 5G uses small cells, thousands of tiny transmitters stuck on lampposts and buildings instead of one giant tower on a hill. It also uses beamforming. In older generations, a tower would broadcast its signal in every direction, like a light bulb. 5G towers act more like a flashlight, identifying exactly where your phone is and shooting a concentrated beam of data directly at it. This reduces interference and makes the network incredibly efficient. The real promise of 5G isn't just speed, it's latency. Latency is the delay between a command and a response. 5G can reach latencies as low as 1 millisecond. This is what will enable autonomous cars to talk to each other in real time, or surgeons to operate on a patient 3,000 miles away using a robotic arm. So, why do we need a 6G? If 5G is so great, why are researchers already working on the next generation? Because we are moving toward a world of Internet of Everything. 6G is expected to launch around 2030, and it will likely operate in the terahertz frequency range. This is the boundary between radio waves and infrared light. At these speeds, the network becomes more than just a communication tool. It becomes a sensor. 6G might allow for human-grade latency, enabling seamless augmented reality where digital objects are indistinguishable from real ones. It could provide a global coverage map using thousands of low Earth orbit satellites, meaning you would have high-speed internet in the middle of the Sahara Desert or the Pacific Ocean. We are talking about speeds up to 100 times faster than 5G. It is the transition from connected things to connected intelligence. Let's talk about the core network, because the towers are only half the story. Every time your phone talks to a tower, that tower is plugged into a massive underground fiber optic network. This is the backhaul. In the days of 1G and 2G, the core network was a maze of physical switches and wires. Today, the core network is virtualized. It's basically a massive cloud of servers running software. This allows for something called network slicing. In the 5G and 6G era, a provider can slice a piece of the network and give it specific rules. For example, they can create a slice for emergency services that is guaranteed to always have high priority and zero lag, while another slice for smart refrigerators might have lower priority. This software-defined nature of the network makes it incredibly flexible and resilient. What about those frequency bands you hear about? The electromagnetic spectrum is a finite resource, like land. Everyone wants the low band because it goes far and through buildings, but there isn't much of it. That's why governments auction off these frequencies for billions of dollars. The high band has plenty of space for high speeds, but it's like a temperamental athlete. It only works under perfect conditions. This is the eternal struggle of the network engineer. balancing range, speed, and cost. Each generation is essentially a new way to squeeze more data into the same amount of space. We've gone from using huge, wide frequencies for a single voice call to slicing those frequencies into thousands of tiny subchannels that can carry millions of data streams simultaneously. Think about the SIM card in your journey across the Gs. In 2G, the SIM card was a massive breakthrough because it made the phone and the numbers separate. You could take your card out of a broken phone and put it into a new one, and all your contacts and your identity went with it. As we moved to 4G and 5G, the physical card started getting smaller, from mini SIM to micro SIM to nano SIM, and now we have the eSIM. This is a chip soldered directly onto your phone's motherboard that can be programmed over the air. It's a move toward a world where you don't have to go to a store to join a network. You just tap a button in your settings. It's part of the broader trend of turning hardware into software. Another major concept to understand is handoff. When you are in a car or a train moving at 60 miles per hour, you are passing through dozens of cells every minute. Your phone is constantly measuring the signal strength of all the towers around it. When the signal from the tower you are currently on gets weaker than the signal from the next tower, the network performs a handoff. In the early generations, this was a hard handoff. The first connection was broken before the new one was made, which is why your calls would often pop or drop. Modern networks use a soft handoff, where your phone talks to both towers at the same time during the transition, ensuring you never lose a single packet of data. It is a seamless, invisible handoff that happens millions of times a day to people around the world. We should also discuss the interference problem. Every light bulb, microwave, and even the sun itself emits electromagnetic noise. Mobile networks have to find a way to screen their data through all that noise. They use coding schemes and error correction. For every piece of real data sent to your phone, there is an extra layer of parity bits that allow your phone to reconstruct the message if part of it gets mangled by interference. It's like someone shouting a sentence to you across a noisy room, and your brain filling in the missing words based on the context. As we move to higher Gs, the math required for this error correction becomes incredibly complex, requiring faster and more powerful processors inside your phone just to handle the incoming signal. What happens in those dead zones? We've all been there. One bar of signal and a web page that won't load. A dead zone can be caused by path loss, which is just the signal getting tired as it travels through the air. It can be caused by shadowing, where a hill or a building blocks the line of sight, or it can be caused by multipath fading. This is when a signal bounces off a building and a tree, arriving at your phone at two slightly different times, which causes the waves to cancel each other out. To fix this, engineers use repeaters and microcells to fill in the gaps. Our modern world is a constant battle against the physics of geography to ensure that every corner of a city has a reliable connection. Let's talk about backwards compatibility. You might have noticed that when you have a 5G phone, it still says 4G or even 3G sometimes. This is because building a new network is an astronomical task. You can't just flip a switch and have 5G everywhere. It takes years to install new hardware on every tower. So modern phones are designed to be multi-mode. They have antennas and modems that can talk to every generation of network. However, as the new networks become dominant, providers begin to perform sunsetting. This is when they shut down the old 2G or 3G networks to reuse those frequencies for more efficient 5G signals. This is why your very old emergency phone might suddenly stop working. Not because the phone is broken, but because the air it speaks to has moved on to a new language. One of the most impressive feats of mobile technology is power management. Your phone is a tiny radio station that you keep in your pocket. If it broadcasted at full power all the time, your battery would last 10 minutes and your leg would get uncomfortably warm. Instead, your phone and the tower are in a constant conversation about power. Your phone says, "Hey, I can hear you perfectly, turn your power down." The tower says, "I can barely hear you, turn your power up." This conversation happens hundreds of times a second to ensure that the network uses the absolute minimum amount of energy required to maintain a connection. It is the reason we can have such thin, light devices that stay connected all day. Then there is the global roaming miracle. When you land in a different country and turn your phone on, it identifies itself to the local network. That network sends a message to your home provider halfway around the world, asking, "Is this person allowed to use our system?" Once the yes comes back, the local network gives you an IP address and allows you to browse. All of this happens in 5 or 10 seconds. It is a triumph of international cooperation and standardized technology. Despite all our political differences, the mobile network of the world is largely a unified machine that allows a person from Brazil to call a person in Norway with zero friction. But it's not just about phones. We have to talk about M2M, or machine-to-machine communication. This is the Internet of Things, IoT. There are billions of devices, smart meters in homes, shipping containers on ships, sensors in farmers' fields, that use narrowband versions of these networks to send tiny drips of data once a day. These devices are built to be incredibly cheap and to have batteries that last for 10 years. They use specialized slices of the 4G and 5G spectrum that prioritize range and battery life over raw speed. This is the hidden network that is currently automating our world's logistics and infrastructure. What about the security of these generations? We mentioned that 1G was wide open to anyone with a scanner. 2G introduced basic encryption, but it was eventually cracked. 3G and 4G added much stronger layers of security, requiring a mutual authentication where your phone proves to the network it's real, and the network proves to your phone it's not a fake tower. 5G takes this to the next level with end-to-edge encryption and more secure handling of your unique hardware identifiers. However, as the networks get more complex, the attack surface grows. We are moving toward a world where the network is essentially software, which means we have to worry about traditional computer hacking and software bugs as much as we worry about radio interference. Another fascinating development is satellite-to-cell technology. Recently, companies have begun launching satellites that can talk directly to an ordinary smartphone. This isn't a satellite phone with a giant antenna. This is the phone you already have. This is the gap filler for the ultimate coverage dream. While it doesn't have the speed for gaming or high-def streaming yet, it ensures that if you are lost in the mountains, you can still send an emergency text or call for help. It is the beginning of a world where no signal is no longer a part of the human experience. Let's dive into latency again, because this is the real secret of the 5G and 6G future. In older networks, when you clicked a link, that request had to travel to the tower, then through various switches to a data center. Then the response had to come all the way back. This created a visible lag. 5G uses edge computing. Instead of putting the servers in a giant warehouse in another state, they are placing small servers directly at the base of the cell towers. This means the data only has to travel a few miles. This is what makes a network feel instant. This is the ingredient needed for things like tactile internet, where you can feel haptic feedback through a gesture in real time, or cloud gaming, where the heavy processing of a game happens on a server, but feels like it's happening on your local device. As we look toward the later years of this decade, we will see the rise of private networks. Large factories, mines, and shipping ports are starting to build their own local 5G networks. They own the spectrum and the hardware. This allows them to have total control over their security and reliability, enabling thousands of robots to move in a coordinated dance without a single wire. This is the Industrial Revolution 4.0, and it is built entirely on the back of cellular technology adapted for the enterprise. What about our health and safety concerns? With every generation, people worry about the effects of radio waves. It's important to understand that mobile networks use non-ionizing radiation. This means the waves don't have enough energy to damage your DNA or cause cellular changes. They are much lower energy than visible light or even the remote control for your TV. The main effect of radio waves at high power is heat, but the power levels used by your phone and the local towers are so low that they don't even significantly raise the temperature of your skin. Decades of research and thousands of studies have consistently shown that living near a cell tower or using a mobile phone is safe within the international guidelines that all providers must follow. The history of the mobile network is a history of S-curves. Each generation starts with a burst of excitement, reaches its peak, and then starts to feel slow as our hunger for data grows. We are currently at the steep part of the 5G curve. We are just starting to see what this technology can really do. In 5 years, we will likely have applications that we can't even imagine today, just as the creators of 4G couldn't have predicted the rise of TikTok or the gig economy. So, where does that leave you? It means you are part of the most connected generation in the history of the world. You have more communication power in your pocket than the entire planet did in 1970. But it's also a reminder of the fragility of our modern world. Our entire economy and social life are now built on these invisible waves. If the network goes down, the city stops. This is why we invest so much in redundancy. Most towers are built with backup power supplies and multiple connections to the internet to ensure that the symphony keeps playing, no matter what. Your phone is essentially a high-tech instrument that is perfectly tuned to this invisible symphony. It is a masterpiece of materials science, silicon engineering, and advanced mathematics. It is the ultimate bridge between the physical and the digital worlds. Every time you see that little 5G icon, remember the 40 years of struggle, the thousands of brilliant minds, and the billions of dollars that went into making that icon appear. We have successfully turned the entire atmosphere of our planet into an information-dense archive that can be accessed from any street corner. The secret to our mobile future isn't just about more speed, it's about intelligence. We are building a network that can sense its own problems and fix them, that can optimize its power consumption, and that can provide a unique experience for every single user. As we move closer to 6G, the network will stop being a pipe and start being a brain. It will be the medium in which our lives happen. I want you to think about the last time you were really off the grid. For most of us, it's a rare and sometimes uncomfortable feeling. That is the power of the network. It has become a fundamental human need, like water or electricity. We have moved from calling people to living with them through these digital pathways. The generations of mobile networks have effectively erased the concept of distance. We are no longer limited by where we are, but only by our ability to stay connected. Your role in this digital transition is to be an informed user. Understand that the network is a shared resource. Respect the balance between privacy and connectivity. And most importantly, appreciate the incredible complexity of the invisible world that makes your modern life possible. The electromagnetic abyss is deep, but it's also the brightest part of our technological landscape. It is the thread that ties all of our gadgets, our data, and our relationships together into one global tapestry. Every generation has had its skeptics, people who thought we didn't need mobile phones or that 4G was fast enough. But human curiosity and our desire to communicate always push us further. From the first garbled analog call on a gray brick to the first holographic video call on a 6G network, the journey has been one of constant, relentless progress. We are a species that wants to talk, and we have built the ultimate machine to help us do exactly that. Stay curious about the waves, stay updated on the standards, and never stop questioning the systems that keep us connected. We are living in a historic era where the very air around us has become sentient with the collective thoughts and voices of billions. You are the user, the driver, and the navigator of this incredible digital machine. Use it to learn, to grow, and to understand the vast, connected world we've built together. The wireless abyss is open, and the next generation of the symphony is just a frequency away. Thanks for taking this deep dive into the invisible backbone of our society with me. Your world is wireless, so respect the spectrum, and it will continue to open doors to a future where everyone and everything is just one packet of data away. Stay connected, stay informed, and keep looking toward the horizon of the infinite network.